Today we're happy to have Upamanyu Moitra from ICTP. He will tell us about entanglement, entropy, and string compactifications.
Thank you very much. I would like to begin by thanking the organizers of this seminar for hosting me here. It's a pleasure to be back here in Chicago after a very short while. And this time I'm going to talk about something completely different from what I had talked about the last time around. I'll be talking about entanglement entropy in string theory in general, and towards the later part of the talk about how this notion can be generalized for string compactifications as well. And this work has been done in collaboration with my wonderful collaborator Atish Davolkar, based on a couple of papers that we wrote a few months back. There's something in progress about which I'll talk towards the end of the talk, and I'll also discuss some unpublished results that we have not put out yet. So let us start with the very basic notion of entanglement. And entanglement essentially is a very quintessentially quantum phenomenon, and it qualifies the failure to factorize a pure state for a generic bipartite system into states corresponding to each of its subsystems. The prime example is the maximally entangled Bell state. If you have a pair of spin half particles, and if this pair is in the spin singlet state, then it's not possible to factorize into two paths for the particle 1 and particle 2, and that's the essential notion of entanglement. And for a bipartite system for which the Hilbert space can be directly factorized like this, the reduced density matrix rho A of the subsystem A can be obtained by taking the pure state of, out of constructing this pure state out of the specific state the system is in, and then taking a trace over the complementary Hilbert space, in this case the Hilbert space corresponding to the subsystem B. And the entanglement entropy can then be found by taking the von Neumann entropy of this reduced density matrix over the Hilbert space of A. And this quantity quantifies the amount of entanglement present in a pure state. And the key player in our story will be density matrices. And in general, to calculate the von Neumann entropy corresponding to your density matrix rho, we usually define a quantity like z hat n, and we take the nth power of the density matrix, and this is some generalization of the Renyi entropy. However, we have information only about positive integral values of this script n, and using this information, we would like to obtain an analytic extension of this function in the variable n. This density matrix rho is Hermitian and positive semi-definite with unique trace. Therefore, this z hat n, you can directly find out from here that it's holomorphic on the right half plane, where real script n is greater than or equal to 1, and it's bounded everywhere. However, if after we have analytically continued this in script n, the behavior for real script n less than 1 on the left half plane may not be so nice, and there can be poles present or other singularities. The von Neumann entropy from this quantity is simply given by the derivative of z hat at 1 and then taking the negative. But the von Neumann entropy is essentially just one number. What we want is more fine-grained information. And for that, the more useful quantity is z hat script n in what we call the physical region, real n greater than or equal to 1, where this function is bounded. And we want to find a suitable analytic extension of this function. And this is fairly well known to in the quantum information theory community as well, and in the quantum field theory literature. It was nicely put forward in a paper of Witten's back from 2018 and 2019. It got published in 2019, but appeared later in 2018.
So can I just clarify? So in the
Yes.
first formula, script n is a positive integer, but then later you say an analytic extension is z hat in n.
Yes.
It makes the n sound like a space.
Sorry, n week. So initially this is defined only for integer n's, integer script n's, but we want to analytical. So this is the only information that we have.
Well, I understand that. Just when you say in n, what does that n now mean?
No, this n is now a complex n.
How complex? It's
Yes, a
complex.
general complex n.
Okay.
Yeah. We'll confine our attention mostly to even real n for our purpose.
So is the first equality defined for n equal 1?
Yeah. For n equals 1, this should just give you the trace of the density matrix, which is unique.
Okay.
So that's all about density matrices in general. But from there on, we want to discuss entanglement in quantum field theory. So physically speaking, there are degrees of freedom in QFT localized at each spatial point. And we can think of trying to partition space into two halves. If we take this whole room as our system, we can divide this room into two parts, which would function as some bipartite Hilbert space of sorts, but I'll mention a caveat shortly. And trying to calculate the entanglement between the degrees of freedom between this half and the other half. However, strictly speaking, such an operation is not valid in continuum QFT because of ultraviolet divergence is present, and the Hilbert space, although it can be naively factorized, it cannot really be factorized or even written as a direct sum over a direct product of Hilbert spaces. But even this naive picture can be made meaningful with some sophisticated machinery, which goes by the name of Tomita-Takesaki theory, as was nicely elucidated by Witten in a paper a few years back. And there's a universal areal or divergence in the entanglement entropy on account of short distance correlations across the entangling surface. And it turns out that the usual quantum mechanical formulation in terms of states is not very useful here. The algebraic point of view is quite useful in describing an entanglement of quantum field theory, because it's really a property of the algebra of observables and not of the states themselves. The algebra of observables for a particular region in space is a type 3 von Neumann algebra. I will not go into the classification of various von Neumann algebras, so I'll just let it be known that type 3 von Neumann algebra is the worst kind there is, and the best kind is type 1.
So no trace. No trace.
Yeah. Type 3 has no trace, no pure states. There's something intermediate, which is type 2, which doesn't have pure states, but it still has trace and notions of entropy. However, we being pragmatic physicists, we try to calculate things all the time. And one of the most popular methods for calculating entanglement entropy in quantum field theory is what is called replica method, in which we essentially take a cut along the entangling region in space and then we glue the manifold together n times with some appropriate boundary conditions, and then do all sorts of manipulation to find the Renyi entropy and then eventually the entanglement entropy. And this replica method is a key ingredient in the proof of the Reed-Takanagi formula by Levkovich and Maldacena, which came a decade back. So this is all for QFT. However, in our world, it's not just quantum field theory that we have. We also have gravity, and gravity changes everything in a very dramatic way. So even if we consider semi-classical gravity on a fixed background, the situation improves slightly on inclusion of gravity. And it was recently shown by Witten and many other people that one gets a type 2 algebra instead of the usual type 3 in quantum field theory. And heuristic arguments, especially from the early 90s, from Susskind, Uglum, Cabot, among others, they have indicated that the divergence of entanglement entropy that appears, that can be absorbed into the renormalization of the Newton constant in canonical gravity. And using this observation, they had argued that the total entropy, it should be finite. However, it's not yet known how to rigorously define an algebra of observables in quantum gravity as opposed to quantum field theory, where there's been much progress. But given the importance of this question, and given that we do have gravity present in the real world, we must at least find an operational way to deal with entanglement in a quantum theory of gravity. And given this audience here, I think I can safely say that we could very well look at the theory of quantum gravity, which is string theory. However, in string theory too, there's no known way to formulate an algebra of observables. More sort of physically speaking, strings are really extended objects. So whenever we talk of entanglement, we think in terms of sharp boundaries, and strings being extended objects, and on account of their soft ultraviolet behavior, dealing with sharp boundaries is quite a subtle question, and we don't know how to deal with that yet. But quite importantly, the structure of string theory is way more rigid than in QFT. There are lots of things we take for granted in QFT, but which we cannot implement in string theory. The replica trick is one example. The replica method doesn't work in string theory because there is no known string background which corresponds to some n-fold cover branched at the entangling surface. That's a part of the problem. However, interestingly, there does exist a very nice method which allows us to make progress, and this is the orbifold method, which was introduced by Atish nearly 3 decades back, and it considers propagations of string in a Zn orbifold where n is an odd integer. So note that I'll be making a distinction between this normal n here and the script n I had used a few slides back. They are related, but they are definitely not equal. So in replica trick, we have a conical excess. In this case, in contrast, there's a conical deficit. And most importantly, this orbifold describes an exact string background. There are indeed tachyons in the spectrum, but these tachyons are localized at the tip of the cone. However, these tachyons, although tethered to this tip of the cone, are nonetheless dangerous, and they will pose a serious problem, and resolving this problem will be the main goal of my talk today. So just to explain the setup, I'll be considering type 2 string theory in 10D. The spectrum obviously includes closed strings. Therefore, gravity is an inseparable part of the story.
So you mean flat space string theory in 10 dimensions?
Yes.
Okay.
So our goal is to be able to calculate the contribution of the one loop partition function to the quantum entanglement entropy. It's worth mentioning in this context that there's a tree-level calculation which gives the classical Bekenstein-Hawking-like term for the entangling surface, and this was nicely observed and calculated by Atish about 21 years back.
Wait, so what is the entangling surface here?
Yeah, I'll make it clear. So this is the geometric picture. So we are taking an order. So in 10D, we write the 10D as R8 times R2. The orbifold action is on the R2, and there's a fixed point, which is the tip of the cone here. And there are strings which are localized at the tip of the cone. And then there are strings that propagate into the bulk. So this is essentially a Euclidean picture. And once we analytically, this corresponds to a situation where my n is an integer. However, from integer or odd integral values of n, we want to analytically continue to a situation where this describes essentially a replicated manifold.
Sorry, what is n in this thing?
So n, it's not visible here. N is the conical deficit in this case.
So your space-time is no longer R10, but R8 cross R2 over
Yeah.
the n.
Exactly.
Okay. Okay.
So this is the R2 over Zn, precisely.
Okay. You're
Right.
studying string theories for this.
Yeah. So to begin with, this is our method. So I'll argue now that this will eventually lead us to considering entanglement in R8 times half of R, or sorry, this will be the entangling surface for, let's say, R plus. So once we replicate this, once we analytically continue this integer n to something like 1 over n, the physical picture is that we will get a replicated manifold. Instead of conical deficit, we will get the conical excess. And this describes a spatial manifold, or this describes the calculation of entanglement between one half space and the other on the real line. Is
Can
this
I
picture clear? Yeah.
Try to
please.
rephrase and see how close it is to what you're saying.
Mhm.
So you start from R2 over Zn.
Yes.
Now you can consider the covering space of this, which would be the picture you draw when you talk about the replica trick.
Right.
And in this covering space, the Cn orbifold singularities are resolved, but you have this higher genus manifold, or more, I mean, you have this replica trick manifold, and you can compute stuff there.
Yes.
And then when you understand how this depends on n,
Yes.
you can analytically continue in n.
Right.
Is this what you're doing?
Yeah. So I'm trying to do an analytic continuation exactly
Okay.
in n, and what so once we analytically continue it to a situation involving conical excess, like in the usual replica trick, we can just see what sort of spatial region is it computing the entanglement entropy of. And that would be simply the half line.
So like, I mean, if what he said was
Yes.
the same thing, like how is it different from the actual QFT calculation? Because it seems to me that
Yeah.
R8 is just playing a spectator.
Yeah, R8 is playing a spectator's role. It's different from the QFT calculation because at least for doing some analytic continuation in any situation, you need to have a consistent background. Here, this to begin with, this R2 mod Z1 over N is not a consistent background of string theory. The consistent background is simply
I mean, it's
I
not
don't
even
even know what-
defined.
I don't even know what it
Yeah.
means.
exactly.
So
exactly.
you probably mean calculating something for many values of integers
Yes.
and finding an
Precisely.
analytic function which
Yes.
interpolates over all these integers.
Exactly.
I guess.
Exactly the point. So this is a consistent starting point from which we would like to perform the analytic continuation.
But like even in QFT, don't you do that? Like
But string theory, unlike QFT, doesn't, at least the lore
Exactly.
is there are no UV divergences.
right.
So you'll end up integrating over a different set of configurations than you do in quantum field theory, because modular invariants will cut off the parts of the integram that correspond to UV divergences in QFT. So, I mean, if this lore that string theory has no UV divergences is correct, and you can define entropy, then you should get a finite answer
Right.
rather than this divergent part.
Yeah, or in other words, thank you very much, Jeff. We are string theory, the formulation of string theory that we are using is an on-shell formulation. Off-shell string theory is much less developed compared to on-shell, and this is an on-shell background of string theory about which we can do it. But I think obviously more guide things to say would be what Jeff just said right now. Thank you.
Why is R2 special?
Sorry, odd.
No, why is R2 special here? Why couldn't I take R4?
No, R2 is special because it really plays the role of the horizon. The I'll be discussing other orbifolds, but it's the R2 mod Zn that can be given a natural interpretation for entropy. There can be other orbifolds you can consider, but they don't admit such a natural interpretation in terms of Renyi entropy and so on.
So you mean we usually think of the external surface of a black hole as a 2D surface and R2 is two-dimensional? Is this?
Exactly.
I mean, my way of saying is more poor, but
No, indeed.
that's
Well, or am I supposed to think of R2 as being the analytic, the Euclidean continuation of R11, and I'm looking at some kind of Riddler horizon?
Exactly. So this is what I was coming to now. So what is the R plus that we are considering? The R plus is nothing when we now further translate it into the Lorentzian picture. This is the region accessible by a Rindler observer. So exactly. So this horizon is what's here at the tip of the cone, and the entanglement entropy that we are computing is the degrees of freedom associated with the Rindler observer.
Oh, I see. So that's why R2 is special.
Yes.
But don't you have the problem that it won't be a solution beyond tree level? Oh, you only care about tree level results.
No, I'll have one loop results as well.
Won't you get a non-trivial? I mean, you're breaking supersymmetry.
Yeah.
He's got tachyons at the tip
Yes.
of the cone.
Yeah.
Yes.
So
What would you get finite results from?
Yeah. So that is the point of
you're
this.
going to have to do a long song and dance to talk about that.
Indeed. So that will be my punchline essentially. Okay. So
You can also study, there was a paper by, I think, Katru, Silverstein, and Polchinski, and then David and Emil and I followed up a couple of papers where you look at, because the supersymmetries and the tachyons are localized to the cone, you can actually look at condensation of the tachyons and figure out where the theory flows to. At least in a theory with n equals 2 supersymmetry. So there's some literature on that, but that's not what he's going to do. He's going to do some mathematical manipulations. Tachyons,
Which
which,
tachyons go away in the,
well, yeah, I
Yeah,
you like to understand
Let's
that.
see.
but-
so
I mean, would you have had a Rindler-like interpretation of some type if you took R4, which would be better than R2? Some case where you wouldn't get tachyons?
sorry, could you go to
Like if you try to continue back to Lorentzian signature at something
Yeah,
bigger than R2. So
You can't really, you can't, there are only some n for which you would preserve supersymmetry.
Oh, that's true, yeah.
Yeah.
You can't take arbitrary and
Yeah.
get away with it.
Yeah, so,
Not
Okay.
even arbitrary integer, you mean?
yeah, not even, yeah.
Yeah,
So I think you, yeah,
you don't get to just freely
no.
mess around, yeah. Okay,
okay. So the one loop string partition function, which I'm calling Z1n without any hat, this corresponds to a toroidal world sheet. However, this is not the space-time partition function which I sort of began with. So the torus diagram is a vacuum bubble in space-time, and the space-time partition function is simply the exponentiation of this quantity. And this z hat is what corresponds to this density matrix directly, the trace of the density matrix. However, for positive odd integral n, z hat does not correspond to an integral n, which is what I had just explained here. This n for the script n is inversely related to this ordinary n. So in other words, if we want to calculate some Rayleigh-like entropy and in the good physical region, so to say, we must have 0 less than n less than or equal to 1, because my physical region, I'll remind you, is script n greater than or equal to 1. This is where the partition function has nice behavior.
So how is the n defined, the straight n in the top equation?
Yeah, this is simply the orbifold n.
No, that was the curly n.
No, the orbifold n is the ordinary n.
Ah, okay.
Yeah, and the curly n, which appears in the
Okay.
density matrix, that's simply the inverse of this n.
So there are definitely some but is the claim that
Yes,
the choosing script n equals 1 over n,
yes,
computing this is the same as computing the entropy of the Rindler horizon if you were to go from Euclidean R2 to
yeah,
Lorentzian R2?
yeah. Formally, there would be the same.
I mean, it's not completely obvious because like if you were in Minkowski space, you wouldn't have the same Z on action.
Yeah. So the point is that whenever we try to calculate entropy, we or in replica trick, we always use the Euclidean space path integral for the vacuum state. And even in ordinary quantum field theory, the space-time interpretation sort of comes later. It's always done in terms of Euclidean path integral. So in that sense, they would be formally the same quantity that we're computing. So the physical region is obviously what we do not expect from string theory, which is this ordinary n, the orbifold n has to be between 0 and 1. So I have to mention here that the story which actually got us to exploring this problem, and this was this very nice paper of Witten's from end of 2018 and published in 2019. He was considering open strings attached to d branes on the Rindler horizon. So it's the classic calculation where one is open string channel and the other is closed string channel. And this open string one loop diagram can be related to the closed string free level propagation between the two branes. It turns out that in this case, open string has no tachyons in the spectrum. And by the open closed duality, there's a good behavior of the closed string in the UV. However, for n greater than 1, when because the orbifold has broken supersymmetry, there are open string UV divergences or closed string tachyons. However, quite magically, they disappear in the physical region after a suitable analytic continuation, which Wheaton had shown. And this is a result that gave us hope for establishing finiteness in closed string theory. And at first sight, the problem seemed to be quite forbiddingly difficult, as Wheaton had also noted in the original paper.
And to do this analytic continuation, Witten actually shows that if you look along the imaginary n-axis, that you have the growth needed for Carlson's theorem?
Yeah. So Wheaton was using Carlson's theorem in an essential way, and he found an analytic continuation which is consistent with Carlson's theorem. And so just for the rest of the members of the audience, so given some function whose values you know only at integers, it's in general not unique if you want to continue it to on the complex plane. But however, as Jeff mentioned, there's something called Carlson's theorem, which has certain boundedness conditions, which essentially makes this analytic continuation unique, and that was a crucial ingredient in Wheaton's picture. But that, while not playing a direct role in what I'm going to say, will very much be there in an implicit way. So I would like to show you the closed string partition function at one loop for orbifolds, and because I'm talking of orbifolds, it's I think quite an opportune moment to note that an inventor of the orbifold is there in the audience. And the one loop function involves the partition function involves the transverse area of the R8 in some suitably regulated way, although it's formally infinite, but we can try to think of some compactification on a very large space. And this involves some theta function. So I'll briefly explain where they all come from, but it's definitely obvious to many of you. So the four theta functions in the numerator, they arise because of four fermions, four complex fermions that are present. And here I'm working throughout in the Green-Schwarz formalism, which are twisted. And in the denominator, the theta functions, there's only one theta function corresponds to a twisted boson on the R2. And this other six eta functions here, they correspond to the uncharged bosons and so on. Where of course tau is the torus modular parameter, and this integration region D is the fundamental domain of the SL to Z group. So that was written in terms of the theta functions, and it's worthwhile to explain how it corresponds, what it corresponds to in the Hamiltonian picture. So this function, which I had called G in the previous slide, it's simply a trace over the twisted Hilbert space with an insertion of some projection operator, and this Q and Q bar are what you find in standard string theory books. This NL, LR are oscillator numbers, and these are the ground state energies. So in the previous slide, there's a sum which I'm calling the twine sum, which goes from L from 0 to n minus 1 with a 1 over n. And this simply affects a projection operation, which means that only Zn invariant states contribute to the partition function. And the tau1 integral in the previous slide, this forces the Virasoro constraint, which simply means that NL and NR have to be equal. And in the space-time picture, the mass squared of the particles is given by the sum of all these quantities. And this is one of the most beautiful things that we realize after starting to study string theory. When we do the integral over the fundamental domain, the ultraviolet region is automatically cut off on account of modular invariance, so that we do not overcount states. And the ultraviolet divergence that could have come, that's automatically taken care of by string theory, and we get something manifestly finite in the UV. However, in the deep IR region for long Schwinger times of the propagating world sheet, there can be an IR divergence, which is obviously more serious because UV divergence more often than not is just a matter of renormalization, but IR divergences we cannot renormalize away. It's usually a signature of something sick, like some unstable potential. And there is an IR divergence which comes from very large values of tau2.
Is this related to the presence of tachyons?
Yes.
Okay.
Yeah, these are tachyons. So now I'm going to talk about tachyons, which has been worrying many of us for a while now. The untwisted sector of the orbifold is essentially like the superstring, and it's tachyon free. However, each of the remaining sector for each all other values of k has a leading tachyon. So just to be sure, I'm just concentrating on some values of k less than n-1/2, which is sort of the halfway point. And there are 3 complex untwisted bosons with this ground state energy, 1 complex twisted boson with this energy, and 4 complex twisted fermions with this energy, which gives rise to this total negative energy minus 2k/n, and there is a factor of 2 because of the 2 sectors. And because this mass squared is negative, this corresponds to a tachyon in space-time. In fact, we find that for large tau2, the leading growth of mod g square, which appears in the modular integral, is of this form. It diverges as tau2 goes to infinity. And just to simplify our life, we know that this k going to n-k symmetry in the spectrum. And for this reason, we can concentrate only for values of k up to the halfway point, that is up to n-1/2. However, it's not only the subleading, the leading tachyons that are there. There are subleading tachyons as well. However, it was quite a surprise for some of us to find that these tachyons have a simple structure in each sector labeled by k. And this being the leading tachyon, we can encode the subleading tachyons in this correction factor. And this has this particular form that it's some finite geometric series, each with unit coefficient.
So what do you mean by subleading tachyons?
Subleading tachyons means that we have this leading exponential behavior at large tau2 here. Subleading tachyons is that this will have okay, you can act with oscillators
Yes.
from the twisted bosons, so that the total energy is still negative. So,
So
it's the most negative energy, and then
one level higher.
yeah, one, or it could be many levels higher.
Okay.
So that is the point, that given this leading tachyon, you can have in each k sector rk subleading tachyons, right up to which this product will have some positive exponential at large tau.
So not only the lowest level
Exactly.
is negative, but also the subsequent one and the few
Precisely.
are still below.
Exactly. And here I'm just this is a finite sum, and this rk depends on which sector k you are in, and this is the largest non-negative integer, so that this is essentially something tachyonic. And it turns out that all subleading tachyons appear with unit degeneracy, like here. And Zn invariance, at least for the tachyons, automatically implies level matching, which is definitely not true for higher non-tachyonic states, but turns out it's true for tachyonic states, and there's some explanation which I will not go into right now.
Can I ask about this unit degeneracy?
Yes.
Right, so you describe these subleading tachyons as I start with the kind of leading tachyon,
Yes.
and then I act with some number of oscillators. on
Yes.
that. But the number of terms where I act with oscillators of total number n
Yes.
that have the same energy is going to be P of n,
Yes.
which is not one.
Sorry.
So in other words, if I had an oscillator alpha minus one, and I had an oscillator alpha minus two, etc.,
Yeah.
I could have alpha minus one squared or alpha minus two.
Yeah.
Those would be two states with the
Right.
same, so that would be degeneracy of two.
Yeah, you are indeed right. But in this case, it so happens that there's only because of level matching, insisting on level matching and Zn invariance, you have something like you can effectively act with only one raising operator.
So you're saying that at each level, there is only one combination of
Yes.
oscillators, which is both level matched and
Precisely.
the n invariant.
Precisely. And you can have n number of this. It's essentially like a harmonic oscillator. You can work with it n times here. So as long as you are interested only in the tachyons, only in the subleading tachyons, this is the case.
It still sounds strange to me. I mean, if you wrote alpha minus two K over N,
Yeah, sorry.
so if K was,
So this is for this range.
right, so I could have K equals one, and I could have that acting twice, or I could have K equals two,
Yeah.
that acting once. Don't those could be the same energy?
Sorry, I didn't understand that. No, I mean,
What, so you're writing the left and the right moving part of the.
yeah, left and right moving
Let
part.
me just look at the left moving part.
Yes.
So I have alpha minus two K over N. Okay,
Yeah. This. Yeah.
right, suppose K is equal
So
to
this is 1 minus 2k over n.
one minus.
Yeah, sorry, I probably didn't. I should have. This is there's a 1 here.
Okay.
Yeah, so
So you
most
have-
of the
Alright.
tachyons are near the midpoint.
K has to be smaller than n, I
Alright,
guess.
exactly.
So you have two, not, I was confused as well, but I think now.
Sorry, I should have put
That one is crucial.
Okay,
Yes.
all right.
Okay, so just as an illustration, this is the leading tachyonic spectrum from 1 to 6 for n equals 13, and the subleading tachyonic spectrum is strongly localized near the halfway point, which is 6 here. So there are 5 subleading tachyons here, only one subleading tachyon here, and no other subleading tachyons for lower values of K. So I now want to do what I call the leading tachyonic sum, in which I approximate all these subleading tachyons only in terms of this leading tachyon, and then sum over all the leading tachyons. And this is the tachyonic contribution to the integrand, and if I just did what I said, I will approximate this correction terms as just 1, and then I will try to sum this from 1 to n minus 1 over 2. There's a factor of 2 here because I also have to count the tachyonic contribution for the other half between n plus 1 over 2 and n minus 1. And this is a nice geometric sum, and this is the answer. And here's the most interesting aspect of the answer, that in the numerator, there's something that appears as e to the 2 pi tau to n minus 1 over n. Because this is tachyonic, for n greater than 1, we definitely want this to diverge at large values of tau 2, and indeed it does. But this expression has no memory of the fact that it came from an expression where n was an integer, and this is analytic in n. And now when we take n to be less than or equal to 1, even at large values of tau2, this is manifestly finite. In fact, this term goes to 0 exponentially fast for large values of tau2.
Can you compute the corrections that you are neglecting in the first iteration of
Yes.
this computation?
But we are still in a bad place because there are subleading tachyons, and they could potentially spoil the story, and it's not obvious that the same thing will work for them. So let us recall that in the subleading tachyonic sum, this is the form of the correction. And in order to facilitate the analytic continuation, it's better to remove this integer rk altogether. So what is the simplest possibility? We take rk to infinity, which corresponds to adding a tower of non-tachyonic states, which will involve some massless states and a tower of massive states. So in terms of picture, this is it. So these were the leading tachyons, these were the subleading tachyons. Now in order to do the sum, I am acting with the same oscillators again, and I'm essentially adding and subtracting the same quantity, so that this describes our tower of states. And now this picture looks much better because now we don't have to care about the value of specific value of k or what happens near the middle point. And this obviously includes all the subleading tachyons as well. So in other words, we are considering this modified sum. This is the subleading tachyonic corrections. This goes from 0 to infinity, and this k sum obviously takes into account all the twisted sectors. So now, for each value of r, we will do a sum in k of this form, where we have added many non-tachyonic states. So now, having interchanged these sums, which is a legal operation because this is an absolutely convergent series, we see precisely the same pattern that even after we have taken into account all the subleading tachyons, this has precisely n-1 over n in the numerator, and which means that as we analytically continue n to less than 1, the tau2 going to infinity limit is finite. In other words, all these tachyons, in spite of having a menacing appearance in the unphysical region, are not actually a physical threat anymore. So let me highlight some of the remarkable features behind the results, and which are in some way just so features of string theory at work. So there are exactly n-1 leading tachyons with unit degeneracy in each twisted sector, and which is an important fact for the nice behavior of the region, because this geometric sum has this nice property precisely because of this reason. The leading tachyon mass squared spectrum is linear in K, and this arises because of some non-trivial cancellations of the parent type 2 theory. It does not happen, for instance, in the bosonic string orbifold, where the energy has some quadratic term in K. And furthermore, the degeneracy of the subleading tachyons in each sector is also unity, and the mass squared spectrum is also linear in K, which contributed to the evaluation of this subleading tachyons in a nice form as well. So this is a full integral in the modular region. So we would now like to split the two terms in a very modular non-invariant way. So this part, which we're calling the remainder part, we can subtract from the full theta function the tachyonic part, and we can add the tachyonic part by hand separately. So now, having removed the tachyons, and since there are sufficient powers of tau2 in the denominator, the integral over the fundamental domain of this quantity is manifestly tachyon free for positive odd integral n. The second integral, of course, diverges, but this is convergent and finite in the region between 0 and n and 1. So for the full integral involving frn, we hope to find some smooth function in the region 0 and 1 by some numerical interpolation method. I'll show you a picture shortly with these discrete points as the known data. So having obtained this sorry, please.
Is this modular? I mean, is there any residue modular invariance when you interpolate the region and less than 1?
Yeah, so that's something that we are considering. It would be nice to have something completely manifestly modular invariant. We don't have that yet, but I'll show you some numerical results at least to show a proof of principle how we could do that, and we might even actually have to even appeal to Carlson's theorem in a numerical way. I'll show you shortly. So this is the tachyonic integral in the physical region, which is completely finite, and this is done over the keyhole region, taking many points, and this essentially gives us a smooth curve, and this is a numerical result. And this saturates as n goes to 0. And this is the finite remainder part, and these are the actual numerical data points which we could obtain after subtracting out the tachyonic term and then doing the full integral over the keyhole region. So now, having known these data points, the goal is to find some nice extrapolation in this region between 0 and 1, which will give us what we want. And it turns out that some of the naive methods like polynomial interpolation might not be so effective in this case, because this being the age of the data points, it's quite unstable under polynomial interpolation. And as Sav also mentioned, I think it would be worthwhile to look for some nice modular invariant way to do the whole integral and analytically continue them. And this is a possibility that we were exploring with a mathematician as well. So this is at least a proof of principle how it could work. And let me now change gears slightly and talk about what happens when we consider compactifications. So
Okay, but before you do that.
Yes.
So the upshot of this is you don't yet actually get a numerical answer for the entropy, because you have to extrapolate to this region numerically,
yes,
and then I guess you'd have to take a derivative and take the limit.
yes.
And you don't know how to do that.
Yeah. So the point is that it turns out that at least with this number of data points, the naive polynomial interpolation, which could have been a way, it doesn't work as well as we had hoped it would, because the convergence is very, very slow. And so we had calculated for values of n up to 41, and obviously it turns out that this will not be enough. So we might have to garner more experimental points up to very high values of n in order to be able to say something about the precise derivative. I mean, from this curve, we could definitely obtain a number, because this is a polynomial interpolation fit, and here we could obtain the slope of the derivative. And from the previous slides, this is much more clear, because this integral is much simpler to do. This derivative we could say with certainty, but from this extrapolation, we are trying to make sure that we have a reliable answer for the derivative, and I'm not just quoting any number yet, but hopefully will be there soon. Okay, so Now we might wonder, because we started with type 2 theory, how generic are these features that we have observed, and whether it's possible to generalize it to other important contexts. A more realistic scenario would be if we consider some less supersymmetric starting point. For instance, compactification on Calabi-Yau three-folds and K3 manifolds would lead to D equals 4 and D equals 6 theories with N equals 2 supersymmetry. While dealing with generic compactifications is difficult, there's an exact CFT description available in the orbifold limit of these manifolds. So for instance, orbifold limit of Calabi-Yau threefold is T6 mod Z3, and for K3 it would be T4 mod ZM for M equals 2, 3, 4, and 6. But here there's some additional complication, because there could be new tachyons from the orbifold twisted states. So in other words, we are taking an orbifold of some parts of the remaining R8, and there could be new tachyons from there. And it's not a priori obvious whether these tachyons, if present, would admit a similar analytic continuation. Oh, by the way, so I think we 5 minutes. Oh, okay, I'll try to.
But the orbifolds you mentioned here all preserve supersymmetry, so
Yeah.
they're not going to give you new tachyons.
No, but there's always a simultaneous orbifold on the R2, and there will be tachyons because of them.
Is that well, okay.
Yeah, so
Is the ZN acting on R2 related to the ZN?
No,
on T6
not-
and T4?
not at all.
All right, so then let's see why they're new tachyons, they're just the old ones.
Yeah. So let me spoil it at first. So there may or may not be new tachyons, but all these tachyons, if present, are related to the ZN being present here. Otherwise,
There was ones.
so working with the Green-Schwarz formalism, it's straightforward to write down the partition function, and I'm not going to explain, and I'm pretty sure this will be obvious to most of you. So I'll talk about the orbifold limit of K3, which is at least one orbifold limit of K3, which is T4 mod ZM. Sorry, and so in this case, there's some ZM untwisted and ZM unprojected sector of the partition function that has this form, and this is the Narayan part of the partition function. And this part has essentially the same tachyon content as the 10-dimensional theory. This is simply a Kaluza-Klein repackaging of the 10D tachyons. Quite importantly, the Narayan partition function for T4 appears in a completely factorized form from the theta functions, and it has no dependence on this orbifold index n. But this net, therefore, this net ZM untwisted tachyonic content admits exactly a similar tachyonic contribution, but it has this new part, which is the factorized Narayan partition function, and the dependence on the compactification moduli enters from here. And this remaining part comes from simply the ZM projections in the untwisted sector. However, as I said, that there can be new tachyons in the twisted sector. For example, let's take Z3 orbifold of T4. We find this ground state energy in various ranges of K over N. And in this range, we see that there are new tachyons which are completely independent of the 10D tachyons, and they are genuinely new tachyons in the spectrum. And even here, we can apply fractionally moded oscillators and obtain subleading tachyons.
Yeah, you corrected the eigenvalue of L0 essentially, because now you don't have a R8 but something else, so
Yes.
it slightly changes,
Yeah.
and something that was positive before may become negative now.
Yeah.
Okay.
Essentially, yeah. So we can have some twisted sector tachyonic contribution written in this form, where for technical reason there's a floor function appearing in the sum, So this is the leading tachyonic contribution, and this is the subleading tachyonic contribution from the fractional oscillators. As a matter of simplification, we can take the lower limit at k equals 1 instead of this floor function, which includes all tachyons but also non-tachyonic states. A similar analytic continuation as before is a sort of similar but slightly different function, which has precisely the same structure as n-1 appears in the exponential. And because of a certain factor here, this turns out to be finite in a bigger domain, which is between 0 and 3. So this tachyonic contribution from P4 mod Z3 has different components. So this contribution essentially comes from 10D in addition to the Narayan paths. And then there are additional contributions because of the twisted tachyons in the new sectors. So I'll just take 2 or 3 more minutes. Is that okay? Thank you. So there can be other examples with or without new tachyons. For example, there are T4 mod Z2 limit of K3. There are no new tachyons at all. So the full answer just comes from the KMD tachyons. For both Z4 and Z6 orbifores, there are new tachyons which admit a nice analytic continuation with some new functions each time. For instance, the T4 mod Z6 orbifore involves this new function as well as some tachyonic partition function associated with the Z3 tachyons. And quite interestingly, because we happen to live in 4 dimensions, it's worth mentioning that there are no new tachyons in the compactification on a Calabi-Yau threefold in the orbifore limit either. And now I'm going to talk about some work that we have been doing and which is quite interesting because it has a bigger payoff. Because the most interesting application of our method would be in understanding entanglement in black hole backgrounds. Fortunately, there do exist black hole backgrounds with an exact worldsheet description. So superstrings in ADS3 times S3 mod P4 background with pure NSNS flux can be described in terms of a Weiss-Domino-Witten model. And in certain regimes of parameter space, the BTZ black hole is the dominant configuration. And we have succeeded in implementing the orbifore method in ADS3 with ZN action on the BTZ horizon. And it turns out that the exact superstring orbifore partition function can be constructed explicitly as in flat space thanks to some remarkable technology available in case of ADS3. The space-time tachyons in this case are localized on the black hole horizon when we take the orbifore. The infinite ADS radius limit produces the flat space partition function with a very nice analytic continuation of the tachyons. And quite amazingly, even for finite ADS radius, the tachyonic analysis it happens can be carried out in a straightforward way. And as has been known since the really nice work of Maldasen, Auguri, and Son from 2001, there are long string divergences in the moduli space which appear at isolated points. But these divergences are not really tachyonic and they don't signify an instability. And furthermore, these contributions are exponentially suppressed compared to the leading order answer, which is consistent with the fact that entanglement entropy is localized near the entangling surface. So I'm at the end of the talk now, and I'll just end with a few implications and speculations. Perhaps the most important question pertains to the information paradox. The strong subadditivity theorem in quantum mechanics is the key player in Mathur's formulation of the paradox, which was subsequently also utilized by amps in the firewall story. And at least we hope we can eventually get to a point where we can make some sharp comments from our calculations. It might also be useful to look at an optional formulation to implement the replica method, because as I explained, the replica method really is not a consistent string background. And finally, as the wild hope or speculation, string theory offers us a natural UV cutoff, and it's worth pondering over whether string theory could lead to something like a type 1 or von Neumann algebra. So that's about it. And before I end the talk, I would like to pay a golden jubilee tribute to the fascinating paper that started our whole fascination with black hole entropy, or this mooted the concept of black hole entropy really. And if you look at the abstract, it seems remarkably prescient and far ahead of time. Actually, when I was giving a talk a few months back, it was my mother who pointed out that this is 50 years of this seminal paper I had forgotten. And we look forward to exploring more consequences of this legendary calculation, and to see if we could contribute to an understanding of entanglement in string theory using our method. So thank you very much.
Do you have any intuition as to what properties of the internal CFT the entropy should depend on when you do these generalizations to K3 or Calabi-Yau? Do you expect it to depend on moduli, topology? I mean, what kind of dependence do you?
Yeah, no, I think they would definitely depend on moduli, as already evident in the orbifold limits in the untwisted sector. So it's not it's for smooth Calabi-Yau manifolds. Presumably, we would not get any of these additional tachyons in the twisted sectors. However,
no, but you could, no, I mean, you could certainly get additional tachyons just because there are operators of low conformal dimension in the CFT of the Calabi-Yau. They don't have to be associated to twisted sectors. But if the spectrum of the theory has things of low enough conformal weight so that that added to the negative conformal weight from the tachyon, then you'll still have tachyons.
Yeah, so that we have sort of briefly considered, but we did not elaborate much on it. And in such cases, a nice Green-Schwarz description is also not available. So we have to do the whole calculation in the RNS formalism with some appropriate GSO projection. And at least for hopefully for generic enough CFTs, we might be able to show conclusively that there will be no tachyons under such an LD continuation, but we are not there yet. And it would be nice to find out what properties the CFTs have to satisfy for there to be no tachyons in the physical domain. Yeah, we hope to look into that probably soon.
But even for a torus, you would expect that for a large torus. Would you expect low lying states where you just get extra vacuum?
Yeah.
And then as you change the moduli of that, this calculation will jump.
Yeah.
In some
No, and in this, so
But then it should be automorphic under the duality group of acting on the moduli, which ought to constrain it.
It's a way of fixing the wave.
Yeah.
Yeah. Yeah, that might.
Yeah, I mean, the Noreen T-duality group
Right.
should act on the moduli dependence, which.
Yeah, that would be pretty non-trivial here. Yeah.
for example, in this case, I think because you're mentioning the torus, so I think the point here is that all the possible tachyonic contributions, they are encoded in the theta function, and this expansion, this has only positive powers of q. So even at generic points in the moduli space for torus compactification, this one would work perfectly because the tachyons are encoded in this function.
I mean, that the theta function part has q to some negative powers.
Yeah.
Right?
Yeah.
So why can't those be multiplied by a q to the PR squared over 2 and still be q to the negative something?
No, they will be negative powered. It's only after analytic continuation. So yeah, that is the point. So probably I didn't emphasize it well enough. So this is the essentially 10D part in the theta function, in the theta and eta functions, and this will have negative paths for sure. That was the whole previous discussion really in 2D, in 10D. But this part appears with with the Narayan partition function completely factorized, and obviously for odd positive integral n, this will still be tachyons, which simply multiply it. So there's no escaping the fact that there will be tachyons, but it's only after the analytic continuation where this part becomes non-tachyonic. This part having positive powers of q will also remain
I
non-tachyonic.
see.
So it's only
You're continuing the first part.
Yeah, so
Yeah.
to make it safe.
Because the second part doesn't contain n.
exactly
That's the point, right? So it's unaffected by analytically continuing.
exactly.
Can I just go back to this last comment about the algebra? Because I thought the recent developments were all around basically being forced to consider a relative entropy when you include gravity, and then getting a type 2 algebra out of that story. Is there some way of interpreting your continuation as some sort of relative entropy, or even in the black hole case with BTZ?
Yeah, that's, I think that would be the hope, but I don't know, at least in the context of string theory, it's I think it's not been done yet.
Wouldn't type 2 be perfectly good? Why do we need type 1? I mean, I thought
Yeah.
type 2, if you have type 2, you have a trace and you can define things. I mean,
Yeah.
type 1 is like finite matrix algebras, right?
No, it need not be finite.
Finite variations of the entropy,
Yeah,
but not the entropy itself is infinite.
yeah.
I see.
So
So type 2 has no pure states.
I agree. Okay. Got it.
Yeah. So eventually showing that in gravity we have a type 1 algebra would be tantamount to solving the information paradox completely. We would show that everything comes from just pure states, but I don't think we are quite there yet.
Well, the question is the same.
did you look for similar computations